We are now moving towards Javier Alonso-García. He's going to give us an update on the VVV and VVV-X view of the innermost Milky Way.
Okay, so I'm going to be talking a little about this VVV and VVV-X CMDs that we can produce, and a little also about how to use them to disentangle and better understand the stellar populations that lie toward the innermost part of the Milky Way, and also how to use the CMDs to better understand the extinction law, the non-canonical extinction law that we can find when we look towards the innermost galaxy. So for the first part of my talk, I'm going to be concentrating on the VVV original footprint. So this is 348 tiles that cover around 560 square degrees in the bulge area and in the inner disk. And in order to better exploit the VVV images that lie in regions of high crowding, the best approach is to go and try to obtain or extract the PSF-Photometry from these images. So how did we do this? So the way that we did it was in every one of the chips of the different VV fields, we ran DUFOT, which is our PSF fitting software, to extract the PSF photometry. Then all of this photometry was astrometrized and calibrated using the CASU aperture photometry information and the information, the astrometric information provided in the images by CASU2. And in the end, we just cross-correlate all the photometry in the different from the different filters. I should mention also that we run the photometry in at least 2 epochs per filter for all the different fields. And in the end, we only retain photometry that appears in 2 epochs in a given filter and in 3 of the 5 available filters, just to get the best, just to be sure that our sources were real sources, there were no spurious detections, and that our photometry was kind of good. Okay, so also, sorry, you cannot see this very well. So in the first, the image in the left is the scene. The second one provides you the ellipticity, and the third one provides you the difference in magnitude between epochs. And if you could be able to see this, sorry for the small numbers, you would see that the images that we used were like were the ones with the best scene. So the average scene that we use from our photometry is 0.75 arc seconds. And then the ellipticity was also kind of small in these images, and also the difference in the magnitude limit between the different epochs that we use for the different filters was also very small. So this is just to make sure that the images that we were using were one of the best ones provided by the VVV. The photometry was very good. The quality of the photometry that we were obtaining was very nice, with small errors. And we also can see that we ran some completeness tests using artificial stars, and we see that the range, the completeness range was very good over the whole, over most of the dynamic range of the camera. we were reaching also, if we compare it with the aperture photometry, we were reaching like 1 magnitude deeper than the aperture photometry, and we also have better better completeness than the aperture photometry. So in the end, we were able to get a final catalog of almost 1 billion sources. 2/3 of them were in the region of the bulge, and 1/3 was on the region of the disk covered by the VVV footprint. So if you plot, or if you take all these sources and all of these sources and you plot them according to their positions in the sky, you get a picture kind of like this. So this is a density map of all of the sources that were detected by the VVV. And there you can see some, for example, you can find the clusters as the small black dots that you can see here and there. So for example, there is one globular cluster here, another globular cluster there, another cluster there. You can also see, appreciate very, very well the shape of the gas distribution with like a high definition map using the different completeness that you are obtaining when looking towards the inner region. So this is the lower completeness here is a signature that the gas is and the distinction is pretty high there.
So can I ask, I mean, you can see the tiles there, right? Is that because of is it the tile overlaps that are producing that?
No, actually, you can see the tiles probably because the a little difference in the completeness when you match all of these and the sensitivity of the different epochs.
Okay, so it's basically different scene conditions give you slightly different depths, yeah, and that shows up in the tiles.
Yeah. Also you have or a similar thing when you look towards the disk area. In here, the disk is just cut in two, but this is just because you can see it, but this should be continuous. So when it finishes here, it continues down here. So there should be only just one plot. And you can see here the windows, for example, of different. You can find windows in the extinction. Like in here, you go much deeper than just down here, for example, or just in here the extinction is lower than in this other area. Okay. So if you are interested in this photometry, it is publicly available now. So you just have to go to the link that we provide in the paper. It takes you to the Vista Science archive in Edinburgh, and in there you just go here, select the cross ID. For the data access, you select cross ID, just select in here the VVV program. The data release is the year 4, the 4th data release. And in the table, you select the VVV PSF-Photometry CYJH KS source, and you input your coordinates, and you will get the photometry that you are interested in. Also, if you prefer to do a freeform SQL search, you can also do it, or you can also email me, and I can try to provide you with the photometry too. So
And your
In
email
this order.
is?
in this order, yeah.
Be careful.
Okay. So if we use this photometry to plot the color magnitude diagrams, we get high quality color magnitude diagrams, and we are able to find the sun, or to discover the different populations that we can see when looking towards the inner galaxy. If you take a look at this first color magnitude diagram of a region in the outer bulge, you can immediately find the nearby KMM main sequence stars from the disk, just in here. You can find farther away F and G main sequence stars here from the disk. And then this is for from the foreground disk, and in here you can find the red giant branch of the bulge stars. You can also see in here some of the blue horizontal branch stars from the bulge, and you can even detect, just in here, some of the background galaxies in the very red part of the color magnitude diagram. Of course, when you try to go to the to lower latitudes, extinction start to kick in badly, and it's more complicated to see some of the, or makes even impossible to find some of the different some of these sequences. But on the other hand, you know, the bulge red giant branch stars are going to dominate, and you can find some of these extensions produced by the extinction. The main one is the bulge red clamp stars. This is due to the bulge red clamp stars, but there are also these two overdensities, one in here just below the red clamp and one above. The origin of these overdensities is a little more complex. In here, it can be produced by the red clamp of the foreground disk, or also it can be due to the AJB bump from the red giant stars from the bulge. The lower overdensity, some people says that can be from the red from the RGB bump of the bulge, but it has been shown that most of it is going to be dependent on a red clamp from the background spiral arm of the disk. So, and a spiral arm that is farther away. If you try to do this, or to do the same kind of color magnitude diagrams from the disk region, you can see also if you are kind of far from the bulge and not in the plane of the galaxy, not exactly in the plane of the galaxy, you can find the disk KMM main sequence stars, like before in here. Here also the disk F and G main sequence stars, and also up here you can see the disk disk red clamp stars coming from the foreground for the foreground disk. If we try to do the same thing, moving a little closer to the plane of the galaxy and also to the bulge, we found that, you know, there are some other red giant stars kicking in and complicating our vision CMD. In the first time, and in the paper that we published last year, we claimed that most of these stars were coming from the Bulge red giant stars, that they were Bulge red giant stars, and that this was mainly the Bulge red clamp. But now I think that it's probably this overdensity is more due to the background disk red clamp stars. So as González and collaborators showed in a recent paper. Okay. So with this kind of CMDs, we have work and or different people from the VVV collaboration. We have been collaborating and trying to get results, scientific results, and some of the results that you can get from this PSF photometry has been, for example, finding the mass of the bulge, or finding or better defining the X shape of the bulge. Also, there are some works that have used this photometry to look into new clusters of stars. And in a work that I have been leading, we have been looking to better understand the extinction law towards the inner galaxy. So what we did here is we concentrated in the 12 innermost VVV fields. There were like 31 million sources there. This is a region of high reddening, high differential reddening. And what we did was we get the color magnitude diagram there. We try to detect the position of the red clamp stars, or the position of the red clamp in the CMD at different colors. And we then fit or did a linear fit to these positions, and that way the slope of this fit give us the selective extinction ratio for this region. Since we have like 5 different colors, we get this selective to total extinction ratios for different filters. And since we also have like I would say the most important color base here, our fitting is the best one that we have till now.
It seems that you have another sequence and one magnitude lower.
Yeah, that's right. It's that overdensity that I was mentioning before. But you see, it's that overdensity. So it's the same one that you can find here, like 1 magnitude before. But for this one, for this study, we just went with the most important one, which is the one that we can attribute to the red clamp of the bulge. Okay.
Sorry, Javier, because you mentioned, I've seen that figure mentioned a lot in a lot of the papers for your extinction law, but it is different when you look in other areas, isn't it?
Wait a second. Yeah. I will go for that.
Yeah.
Okay, so this is for the inner part of our galaxy. So as I was mentioning, we have different filters. So we have the extinction law at with different colors. As you can see, the values that we are obtaining are smaller than the ones obtained using the canonical law from Cardelli, and they are even smaller than the values found by Nishiyama and collaborators in some cases. So in addition to that, we were able also to check on on the extinction law there, and we found that the extinction law was steeper than previously thought. The alpha value that we are finding is around 2.5. The values from Cardelis is closer, is below 2. So our extinction law towards the galactic center is, as I am saying, steeper than previously thought. Also, there was, like Phil was mentioning, there were some talks that, you know, this extinction law is different for different regions. And in order to check this, what we did was divide our field in 4 different and equally sized quadrants, and we repeat the analysis that we did for the whole region for these individual regions. And what we did find indeed that the extinction is kind of different for different regions. I mean, up here is closer to 0.38, 0.39. Here is closer to 0.46, and here is 0.41. So extinction is going to change in a smaller region. So you should be careful when you are trying to use a universal extinction law for the bulge, for example.
Which are the errors on this individual numbers?
Actually, I think that the measurements that you are seeing here, the first error is the statistical error, just from just fitting the line there. The second error, I try to include there the variations that you can find, the variations that you can find in here. Okay. So in the different regions, you are finding different values. So getting all of them will give you that error. So the next step would be obviously to extend this to a bigger area and to examine this extinction in smaller regions of the sky. So I try to start working on this. And here you can just see the color magnitude diagrams of regions of 1 by 1 degree in the sky. And you can immediately see the problems that we are going to be facing. And it's that the differential extinction, because the regions now are much smaller, there are not so much differential extinction in some cases. So you can, for example, here, so you cannot have like a lot of a big baseline in order to study the differential extinction. So it's a little more complicated. It's even more complicated if you go to longitudes that are farther away from the center, in which you have even a smaller number of stars in the red clump. So in there, it's kind of complicated also to try to follow where the red clump is and find what the extinction law is. Also, well, here at least you can get a little help from the stars that are in the background. So these are red clump stars for the background disk. So maybe you can use the background disk also to study the extinction. So this is something that I wanted to discuss with you this afternoon, so we can talk a little about, you know, how to try to look for extinction in smaller, for the extinction law in smaller pieces of the sky.
Are the diagrams placed in galactic coordinates? I mean,
yeah.
Longitude and latitude.
That's right. So this is 0 latitude, okay. 1 latitude, and -1. And then the latitude, this is -4, -5, -6, -7, -8. And if I go back, this is 0. Okay, so
Okay.
0, -1, -2, -3, -4, until -10 up here. Okay, so something to discuss this afternoon. Okay, so now for the last minutes of my talk, I'm going to concentrate on the VVV-X area. And as Marian has mentioned, as Marian and Dante have mentioned, we have already covered the whole VVV-X area with the multicolor photometry. And I have started working on the PSF photometry, running our pipeline there. And in the end, now, since we only have 3 filters, what I did was retain only photometry from sources that appear in one epoch. Of course, we only have one epoch in J and in H. So also I just take one epoch in K and retain that photometry if the source appears in the 3 filters at the same time. And these are the numbers that I was obtaining for the sources. So in the end, if you add this up, you almost get 600 million of sources more. So now if you have the VVV plus the VVV-X whole survey, you are getting close to 1.5 billion sources that we are able to find there. With this proof photometry, with the VVV-X PSF-Photometry, we can start building color magnitude diagrams and looking for new scientific goals. Like, for example, we can try to look to the Sagittarius dwarf galaxy and try to, we are imaging the center of the galaxy. Here you can see the contribution from this dwarf spherical galaxy, and we can also try to follow its tidal streams. We can also look for things like we have done with the original VVV footprint. We can see here the difference in magnitude of the red clamp or even the double red clamp with the VVV. But now we are also covering the VVV with the VVV-X area. We are covering the northern part of the Bulge, and we can find also these signatures of the X-shape. We can also try to look for clusters. There are 17 known globular clusters that are in the VVV-X area, in addition to the ones that, of the 36 that were in the VVV original footprint. So we have data for 17 known globular clusters more. We can also start looking for new clusters, like Jura is doing for open clusters. I think that Sebastian is going to show some of those new results. Dante has been looking for new undiscovered globular clusters also there. So there's a lot of things to do, but now just know that we have also this first attempt of VVV-X PSF-Photometry. And these are ideas that we can also discuss. So Dante was asking for things to do with the VVV-X. Here are some. We can start this afternoon writing papers. And with this, I'm going to finish. And thank you for your attention. And if you have any questions, please, or suggestions, please let me know.
Thank you for that. So thank you. Anyone?
How long it took you to send the data to VSA? How effective was that?
It was not so complicated to give them the data. Then they had to create the tables the way that, you know, in order to input them in their system, it take it a little longer because they have to do some management with the data that I provide.
But it was half a year.
Yeah, for them it was several months, but you know, just sending them the data, it was no time. I mean, in a few days they can download.
Because for this it will be more or less the same.
Yeah, I would say so. But I would like to work a little more on the VVV-X
Before
photometry before sending it to them, because I need to change some parameters.
Okay, now.
So Javier, I think I missed the information, but I always wondered about the completeness for the VVV-X version, and also those numbers that you show, the total number of you computed those numbers based on what threshold, from 2 sigma, 5 sigma, what criteria did you use?
So no, the way that I calculated the completeness, or we calculated the completeness test, because this was also mine's work. So we did artificial star tests.
Okay.
And we inject stars at different magnitudes in 3 different regions of the VVV original footprint.
Okay.
And just then we ran our photometric pipeline and
then
check,
compare the.
yeah, and check which ones we were recovering.
Which one did you finally use? Just has it been detected or not, or additional?
I think it was a detection, and within some, I don't remember now which photometric difference.
And what was the top level for the errors? So you probably use some cut in order to define these numbers. I'm asking you because this is a very critical, so you can go upper on this as you wish, but in some you need.
No, I think, yeah, I don't remember exactly the cut limit, but we did some. They have to agree the photometric the photometric values that the magnitudes that we were recovering had to be within some
a couple of different scenarios, either an absolute offset or, let's say, within 0.1 magnitude of the original input magnitude. And we also did one test where we said it has to be within 5 times the photometric error of that star.
Yeah.
So, but that certainly shifts things, because on the both ends, on the bright side, because close to saturation, the error is larger, so you lose a lot of the sources on the bright side, on the faint end anyway.
Yeah.
But
anyway, the numbers are pretty impressive. So.
No, and I can. We also make comparisons with the aperture photometry, and you know, we were going deeper, or we were detecting deeper, like 1 magnitude deeper than they were, and the completeness there was also higher. I mean, we were recovering for a given magnitude range, we were recovering more stars than they were.
You get 18 magnitude in K there. If you allow for only 1.1 magnitude offsets, the completeness from the aperture photometry pretty much goes down to single-digit percentage.
We had a student there in ULS. He made this postgrad using one of the VVV original footprints, and it was quite a lot of work for him. And it's very tricky. There are some details that but of course we are talking about 1 degree or something, and then you were talking about a huge area. So how to handle this is nightmare. Yes.
Another quick question or comment? Yeah.
I have a question that I don't, you may have touched on this a little bit, but you know, there's this battle going on about whether there's an X-shaped bulge. And the counterclaim is that this second component that you see is actually also red clumps, but helium enriched, and therefore brighter by 0.4 magnitudes.
Mm-hmm.
Do you have an opinion or on this issue, or do you think your data can?
I think that the person that is sitting just by it has also an opinion, but I would encourage you to read Oscar Gonzalez paper on the VVV on the X-shape that using our PSF data, in which he demonstrates that, you know, it's in order to have the helium enhanced X-shape, well, the helium enhanced explanation for the X-shape is tricky. It's too tricky. It's easier to understand this difference in the red clamp position, or even the double red clamp in some. So you can see here that the red clamp is at a higher magnitude. Oh, sorry. Than in here, and in the at these longitudes there is like a double red clamp. So there is one here, and there is another one there. So it's easier. The geometric explanation is much straightforward, just having an X shape than, you know, having this helium enhanced thing. So I encourage you to
educate me later. I want to understand this.
Okay.
So I would appreciate hearing the argument, because I think I can make the counter argument. I just wanted to see what people thought about this issue.
Maybe.
I think that essentially is that if it were a stellar population effect, like helium enhanced versus helium normal, there shouldn't be a spatial variation.
Right. In other words, it
And
should
you
always
see
be the same
coherent
offset.
spatial variations. So it's something that has to do with the geometry and not with the stellar population.
Mhm.
Because if it had to do with the stellar populations, then it's much more difficult to explain why they are helium enhanced stars in some parts of the sky and not in others.
Yeah.
So
Yeah, and now we have the
it's much
kinematic data
simpler
as well.
explanation.
I'm sorry.
And now we have the kinematic data as well.
Right.
Yeah.
Which
Yeah, I mean, it
From
just shows the radial
yes.
orbits and everything, radial motions of the X, you know, so it's.
No, sorry, I think that this diagram is very straightforward in the sense, if you take a look on the scales, and if you think that, okay, if the colors are, let's say that just mainly due to distance, different from distance or whatever, actually this figure would be much better, I guess, if you have used the same scales on all the, because if you could, I understand well this, you can see clearly the difference on the distance.
Sorry, what do you
In
mean
the-
the same scale?
The colors.
The colors?
Yeah.
Okay, yeah. Okay.
You clearly see that, for example, for the 0.7 degrees, let's say J
Well,
minus K1, and then 0-7 is 0.7.
I think, sorry, hold on 1 second. I think that the scale is the same. The color are not the same because the extinction is different, but but the colors the color range is the same. It's the
the scale is
yeah.
wrong. Okay.
the scale is right. So the scale is the same up and down, even if the colors are
Because in the top diagrams, you don't have the zero.
yeah. The top
This
there
is why I'm saying.
No, it's not. There is no zero because in order to get, but you know the range is 1.3 magnitudes in color.
Okay.
So it's the same. It's the same down and up. The difference between the why
It's
they
0
did
point
it,
for each.
because the extinction is different.
Yes, but if you think of this thing that Benjamin was mentioned about the X shape, if you think of this virtual entity as a real one, you would say, okay, this has some kind of extinction in the middle of the galaxy. So it's not localized one, it's bigger, it's a bigger structure. No? So you could see, you could interpret this as an effect from this kind of X or whatever shape. I don't know if I'm
we can talk about this a little
but
bit.
this is very interesting. It's a very interesting.
I think that this X shape is going to join in us for the intermeetings. So I think
Sorry to raise it.